Fast radio bursts, or FRBs, are one of the most mysterious phenomena in the cosmos. Imagine flashes of energy erupting across the sky, releasing as much energy in a fraction of a second as our sun does in an entire day. These bursts are invisible to the human eye, but they light up radio telescopes with powerful signals, leaving astronomers both astonished and puzzled. FRBs were first discovered by chance, and their rapid, unpredictable nature has made them incredibly difficult to study. Thousands of these bursts occur daily, yet pinpointing their exact source is a challenge. For years, scientists have wondered what could produce such intense bursts of energy. Theories have ranged from stellar explosions to massive black holes. But thanks to recent advancements, researchers now believe they may have found a crucial piece of the puzzle. FRBs seem to be linked to specific kinds of galaxies. By mapping the origins of these bursts, a team led by astronomer Kriti Sharma has discovered that most FRBs come from massive, star-forming galaxies rich in metals, elements heavier than hydrogen and helium. This discovery hints that certain cosmic environments might be perfect for producing the exotic sources of FRBs. But what exactly could be causing these bursts within these unique galaxies? Astronomers have made a breakthrough discovery linking fast radio bursts, FRBs, to their home galaxies, and it's shedding new light on where these powerful cosmic flashes come from. Recent research led by Kriti Sharma and her team has mapped the origins of FRBs to massive, star-forming galaxies, particularly those with a rich composition of elements beyond hydrogen and helium, what astronomers call metals. These metal-rich galaxies provide a very specific environment that may hold the key to understanding what powers these sudden, intense eruptions of energy. But why are metals important here? In astronomy, elements heavier than hydrogen and helium, such as carbon, oxygen, and iron, play a critical role in star formation and evolution. In these metal-rich environments, stars often form in close pairs, or binary systems. Over time, the larger of these stars can begin to draw in material from its companion, sparking a complex process that may lead to the creation of some of the universe's most magnetic and mysterious objects, magnetars. Magnetars are a type of neutron star with magnetic fields so powerful they can reshape the matter around them. Imagine a star whose magnetic field is hundreds of trillions of times stronger than Earth's, intense enough to tear atoms apart and unleash bursts of energy that ripple across galaxies. It's this extreme magnetic environment that astronomers now suspect could be the origin of FRBs. The idea is that in these metal-rich galaxies, massive binary star systems may merge or evolve in a way that gives birth to magnetars, and with them, the short, explosive pulses we observe as FRBs. This link between FRBs and magnetars within metal-rich galaxies represents a major step forward in solving the FRB mystery. For years, scientists have speculated about the origins of these bursts, but pinpointing them to specific galactic environments is an exciting new piece of evidence. It not only strengthens the theory that magnetars are behind these bursts but also suggests that the environments within certain types of galaxies play a crucial role in creating these powerful cosmic events. So what else could this discovery reveal? The link between FRBs and metal-rich galaxies may point to broader connections in the universe, potentially reshaping our understanding of how extreme objects like magnetars form and behave. Now that scientists have traced fast radio bursts, FRBs, back to metal-rich, star-forming galaxies, the next piece of the puzzle lies in understanding the extraordinary objects thought to produce them, magnetars. Imagine a star so dense and magnetized that it can warp space around it, a force of nature packed into an object just a few kilometers wide but weighing more than our sun. This is a magnetar, a type of neutron star left behind after the explosive death of a massive star, known as a supernova. Magnetars are some of the most extreme objects in the cosmos, with magnetic fields a trillion times stronger than a standard refrigerator magnet, strong enough to crush the atoms around them and produce violent eruptions of energy. And it is these bursts, scientists now believe, that might create FRBs. Yet, not all magnetars are alike. Most neutron stars form when a massive star collapses and goes supernova, but researchers are finding that the magnetars linked to FRBs may have a different origin. In metal-rich galaxies, binary star systems, where two stars orbit each other closely, are common. As these stars evolve, the larger one begins to siphon material from its companion, drawing mass and energy in a kind of cosmic dance that brings the two stars closer together. This intense gravitational interaction eventually leads to a stellar merger, creating a new kind of magnetar that's been supercharged by the mass and magnetic energy transferred during this fusion. This stellar merger process is not only rare but also incredibly violent, amplifying magnetic fields to levels so extreme they can shatter atoms. In these fused, high-energy states, magnetars have the power to release bursts of radio waves strong enough to be detected across the universe, FRBs. Unlike the magnetars formed in typical supernovae, these fusion-born magnetars have unique characteristics due to their formation process. Their amplified magnetic fields are believed to produce the intense, brief flashes of energy that we observe as FRBs. The role of metals in this scenario is critical. Metal-rich environments are thought to enhance the chances of creating binary systems that eventually merge, providing the perfect setting for this rare phenomenon. As these magnetars erupt with energy, they may do so sporadically, leading to the mysterious variability of FRBs. Some FRBs repeat, while others occur only once. One possible reason for this difference lies in the magnetic stability of each magnetar. Magnetars born from stellar mergers might experience bursts of instability over time, causing repeated eruptions, while others could have a single explosive episode before stabilizing. This discovery brings scientists closer than ever to understanding not just the source of FRBs but also the life cycle of these extraordinary magnetars. The finding challenges conventional ideas of how neutron stars and magnetars form and suggests a complex, interconnected pathway involving metals, binary stars, and extreme cosmic events. It opens a fascinating new frontier in astronomy. How do these magnetars evolve over time, and what else might they reveal about the workings of our universe? If magnetars are indeed responsible for fast radio bursts, FRBs, then understanding how these unusual stars evolve becomes crucial. Magnetars created by the fusion of binary stars have a unique formation story that sets them apart from typical neutron stars formed in standard supernovae. In metal-rich galaxies, where elements heavier than hydrogen and helium are abundant, stars are more likely to evolve in close pairs, or binary systems. Over time, the larger star pulls material from its smaller companion, sparking a dramatic exchange that brings the two stars closer together until they eventually merge. This merging process unleashes immense magnetic energy, resulting in a type of magnetar with unprecedented power. What's extraordinary is how this fusion-born magnetar's magnetic field, one of the strongest forces in the universe, might evolve. As the star's field twists and contorts under extreme pressure, it occasionally destabilizes, releasing intense blasts of energy. These blasts are what scientists now believe could cause FRBs. In a way, these magnetars are like cosmic batteries charged by the extreme gravitational and magnetic forces of the merger, releasing surges of radio waves visible across the universe whenever their magnetic fields reach a breaking point. But here's where things get even more interesting. Binary systems tend to have longer lifespans than isolated stars. This extended life cycle means that fusion-born magnetars might continue to erupt with bursts of energy for far longer than magnetars formed from single stars. As these magnetars age, their magnetic fields become more complex and perhaps more prone to sudden instabilities, which might explain why some FRBs are repeaters, flashing multiple times from the same source, while others are observed only once. The impact of a metal-rich environment on this process is crucial. In galaxies dense with heavy elements, the presence of metals accelerates the fusion process, effectively fueling these stellar pairs and enabling the mass transfer necessary to produce a fusion-born magnetar. It's a scenario that appears to align perfectly with the type of galaxies linked to FRBs. When these magnetars finally explode with a burst of energy, the FRB carries with it clues about the star's environment, its magnetic history, and its unique formation pathway. Yet, many questions remain. Could there be other cosmic factors at play, or perhaps other types of magnetars that create FRBs in ways we have yet to understand? As scientists study these metal-rich galaxies and the unique magnetars within them, they hope to uncover even more clues about the mechanisms behind FRBs. The mystery of what causes these intense bursts might be one of the biggest astronomical puzzles of our time, leading us to reconsider what we thought we knew about how stars die, merge, and even communicate across galaxies. This discovery hints at a universe full of surprising pathways to stellar evolution, where metals, binary systems, and extreme magnetism intertwine to create some of the cosmos's most enigmatic phenomena. The possibility that we're witnessing stellar remnants communicating through brief, intense flashes opens new avenues for exploring not just where FRBs come from but what they mean for our understanding of life and death in the universe. Despite all that scientists have uncovered, fast radio bursts, FRBs, remain a cosmic mystery with lingering questions. Why do some FRBs repeat while others flash only once? Could there be other mechanisms, besides magnetars, responsible for these powerful signals? Researchers are eager to dig deeper into the life cycles of magnetars, hoping to unlock answers to these questions. Each FRB might carry the imprint of its unique environment, leaving traces of its galactic home, the fusion of stars, or perhaps even unknown forces at work. The more we learn about these bursts, the more they seem to challenge our understanding of the universe's extremes. Looking ahead, astronomers are developing advanced telescopes and observatories to catch FRBs in real time, aiming to track them with even greater precision. New data from these instruments could reveal hidden patterns in FRBs, shedding light on the role of magnetic fields, stellar mergers, and cosmic metals in shaping these bursts. But FRBs are more than just astronomical curiosities, they are windows into the most powerful forces at work in galaxies far beyond our own. By following these signals, scientists may uncover new laws of physics or even clues about the formation of galaxies and the nature of dark matter. As we continue to tune into these fleeting signals, we're reminded of just how much remains undiscovered. FRBs may hold answers to questions we haven't even thought to ask, pointing us toward a universe that is richer, stranger, and more interconnected than we can imagine. If you're as captivated by these cosmic mysteries as we are, subscribe and join us on this journey. From fast radio bursts to the universe's most extreme phenomena, there's a vast frontier to explore, and every discovery brings us closer to understanding the hidden workings of the cosmos.